Hello to everyone here, and aloha to everyone joining us online. I am going to talk today a little bit about a feature that came in Java 7 and has continued to evolve called MethodHandles. Quick intro, I'm Charles Nutter, Charlie to my friends. We learned on Sunday that Charlie really doesn't surf, so we'll have to make a few more trips back to improve that. I have been working at Red Hat for about 5 years now, working full-time on JRuby, JVM language-related work, experimenting with the new APIs like MethodHandles, and actually working on JRuby full-time for over 10 years now, almost 11 years. It's been quite a ride. So what are we going to cover today? I'm going to talk a little bit about what are MethodHandles, what is this API actually used for, what do we do with it, why do we need MethodHandles? Initially it was supporting dynamic languages and so on, but they have grown to be much more practical and have many uses on the JVM. We'll talk a little bit about what's changed in Java 9. We got a bunch of new handle adapters, and we've got some support for working with variables more directly. I'm going to talk about an API that I maintain that helps my sanity when I'm dealing with method handles called InvokeBinder. And then maybe we'll see one or two little crazy things that we can do with method handles that might illustrate how powerful they are. Okay, so beginning, method handles. So here's a little bit of history. Like I said, I've been working on JRuby full-time for about 11 years. In 2006, Sun Microsystems got really interested in alternative languages on the JVM, especially dynamic languages, because at this point, Ruby was getting really big, Rails was big. 2006, everyone's freaking out about Ruby on Rails. People are leaving the Java platform in droves to go do other languages. Sun was like, yes, we need to get these people and lock them into the JVM again by working on more language support. And so we had this renewed interest in getting languages to work well, especially getting dynamic languages to work well. And it turned out that there had been some interest in this before. There was a JSR for a feature called InvokeDynamic that had kind of stalled out. It didn't really figure out a good way to get this into the JVM, didn't really have the justification that we needed for dynamic languages on the JVM. So it's time for a reboot. Sun brought in the JRuby guys, Groovy was getting very popular, the Jython guys were working again. Let's see if we can do this again, try and make the JVM a good place for dynamic languages. So what did we need? And by we, I mean mostly the dynamic language folks that were involved at this point. Well, we needed to be able to call methods dynamically. That's an obvious one. We all had very different class structures. Groovy, for example, would generally use the Java class file class structure, but they also had their meta object protocol, so you could add methods and remove methods to existing Java types. In JRuby, all classes start out as just an empty hash, essentially, and you fill it in with key value pairs, names, and functions. That's what a class looks like in Ruby. You fill in the blanks, essentially. So we all had different ways of doing calls and different ways of representing types. We needed a way to dynamically call those methods. In Ruby, at least, we also needed a way to dynamically assign fields and constants. Constants in Ruby are lazily assigned only when you run the code the first time, and so we needed to be able to sort of defer that. Rather than like a static final in Java, we needed to be able to run a bit of code, generate this constant value, and then have it optimized as if it were literally written in the code to begin with. So optimize it more like a static final. And we needed this all to be fast. Obviously, if we're going to do dynamic languages on the JVM, we'd like to take advantage of the JVM's optimizations and the JIT that's underneath it. So we wanted to be able to do dynamic calls, dynamic variables, dynamic constants, and have it all eventually look like it's just written as Java code when it optimizes down to native. And that became JSR 292. We rebooted the InvokeDynamic JSR. So there were two parts to this. The first part, which I won't cover today, is a new bytecode that was added to the JVM. For the first time in 20 years, added a new bytecode called InvokeDynamic, which is essentially like a user configurable bytecode. Whenever the JVM would run into an InvokeDynamic in the code, instead of doing a specific thing like calling a method or adding two numbers, it would hit your callback. Your callback would say what exactly it should be doing at this point. The JVM would insert that back into the code and then optimize the whole thing. So dynamically, you could decide what this bytecode would do. That was the magic of InvokeDynamic. And in order to support that, in order to be able to put all the plumbing behind that InvokeDynamic bytecode, we have the MethodHandle API. And that's what we're going to be talking about here today. So what do we have in the MethodHandle API? Well, it's very similar to reflection. So at the beginning, the first thing you want to do is you get a lookup object. This lets you look up methods and fields and so on other classes, sort of like using Java Lang class to do reflection. Method type is used to box up a representation of a return value and argument types. So you take a lookup object and you take a method type, and then you can go find the method that you're looking for on some class. Methods, fields, array accesses, these are kind of the endpoints of your method handle chain. They're a function call, or they modify something in memory. These are where the visible side effects of calling a method handle actually would show up. And then a whole bunch of adaptations. So MethodHandles class, Java Lang invoke MethodHandles, provides additional wrappers, additional adapters. You can reorder arguments, you can do exception handling, and so on. We'll show some examples of that. And so what you've got your endpoint, your final direct handle that points at a method or a field. You wrap all of these different adaptations and conditions and logic around it, and then you get a method handle tree that you can call. It's this magic function that the JVM will optimize as if it was written as Java code or generated as JVM bytecode. Like I say, it's very similar to reflection. So a lot of the use cases that we have for reflection apply here. If you want to dig into the internals of an object that you don't necessarily know the structure of, reflectively call methods, reflectively pull data out of it. If you want to build a framework where you can pull in user-defined code and run it. So for example, a testing framework that you might want to be able to exercise code that you've never seen before, code that you can't statically compile against. Good opportunities for method handles. Metaprogramming, generating adapter code based on the structure of classes and methods that you see. So all of these things generally apply to method handles, but method handles do this much better. There's lower overhead. Reflection has quite a bit of overhead for all the argument checking, error handling, and so on. And the JVM can see all the way through method handles, whereas with reflection, many times it can't optimize those. It becomes a hard barrier between two optimized pieces of code. You don't get as much of that optimization potential. Also in Java 9, I'll talk about later, it's starting to replace some of the unsafe operations, the sun-misc unsafe atomic operations, for example, or the fencing operations for memory barriers. These are now starting to be exposed as part of the MethodHandle API. All right, so we'll walk through some of the basics of using this API. Like I mentioned, it's similar to Java Lang class, which is where you do your reflection from. We start out with a lookup object. There's two different ways to get a lookup object. The top one, just the plain lookup call, gives you a lookup, a reflector object, that can see everything this class can see. So it can see private methods, private fields. It can see package visible things. So wherever that lookup method is called, it's like that's the visibility that goes along with this. So if you want to give another library or give a class access to some of your internal methods, you can use that special lookup class. Typically what you'd be using though is the public lookup. You just are interested in public fields, public methods, public state of the classes that you're working with. And then this kind of helps you ensure that you're only doing public accesses, or if you need to dig in deeper, most of the access checking is already done in that special lookup object. So we've got our lookup. Now we need to have a method type that represents a return value and argument types. So here we have three different versions of methods that we're looking up. The first one, the lookup find static here, we're getting the getProperty method off the system class. And the method type for that is that it returns a string and it takes a string. Simple enough, right? In Java Lang class, it'd be getMethod or getDeclared method, getProperty, and then you would just say it takes a string. So very similar API use at this point. Again, find virtual. This is a method that's called against an instance of an object, not a static method. We've got the add method, which takes an object and returns an int index for where it was added. And then at the bottom, we have find constructor. So if we want to construct objects, same thing as we would do if we did get constructor from Java Lang class. So we've got our method in hand. We've got our method handle that points at something we can call. We also have opportunities to look up fields. So here, we're just getting the static getter for the system out field, which will get us a print stream. And just like a Java Lang reflect field, now whenever we call that, we can get the out field. Of course, is equivalent one for find virtual getter for finding or find getter, I think it's called, for finding it against the particular object. And so then we have have this all put together, and this is largely where reflection would stop. You would get a handle to a method, or you get a handle to a field, and you could pass that around and you could use it to call that method, but you still had to do a lot of your adaptation. If there was argument manipulation you needed to do, if you needed to two-string something before you called it, if you needed to do argument casts, you would need to do that sort of thing ahead of time. So MethodHandles also added some additional ways that you can enhance that target handle. So here we're taking the getProperty method handle, which just does the getProperty call, and we're binding it permanently to java.home. So now we have a method handle that does getProperty java.home, all as one callable function object. Again, the JVM will optimize all the way through this and turn it into one piece of native code once you actually call it. Similarly here, we've inserted the load factor of 1.0. We don't want our hash to grow quite as quickly for the hash constructor here. And so now we have a hash constructor method handle that will use a load factor of 1. All right. And then, of course, we want to actually call this so we can invoke it. And there are a couple different ways. So quick notes on how these work. There are a couple different ways that you can invoke a method handle. If we talk about reflection, Java lang reflect method.invoke, for example, does a lot for you. It's one of the reasons that it doesn't optimize very well and doesn't often inline, because it has to do all those type checks every time. It has to do access checks every time. It's trying to make sure that any exceptions bubble out and get rewrapped. So it really hides the fact that you're doing this method call, and especially hides it from the JVM. With method handles, we have some more direct options. Invoke with arguments is probably the most equivalent to the reflection invoke. It does some argument casting for you, boxing and unboxing of var args, and so on. MethodHandle.invoke reduces some of that, takes some of that extra overhead out of there. If you know you're always calling with the right types and with the right number of arguments, you can use this. InvokeExact is the lowest possible level. The argument types in the Java code have to be exactly what is expected on the other end, even to the point of having to cast, say, an array list to a list. If you try to call it with array list and it expects a list, it will not work. It does not handle the casting for you. But that can also give you opportunity to have the fastest possible direct invocation to that method handle. All right, but generally invoke with arguments, invoke are going to do pretty much what you expected from reflection, and you can expand from there if you need a little bit more raw support. So an easy way to see how method handles can be used and how they can be composed is to go through a piece of Java code and essentially rewrite it all as method handles. So here's a very simple hello world, a little bit more advanced than a hello world because we're taking in an argument from the command line and building our hello string based on that. Simple enough code for anybody to follow through here, so we'll see what this would be in handles. First of all, like we saw before, we've got our system out get. That's going to be our static getter. So we say get the system out field, which is a print stream. Now we have a handle for accessing that stream. If we go down to our array access, we can say MethodHandles.ArrayElementGetter. We know we're going to have a string array coming in. Give us a method handle that can be used for getting values out of a string array. We have the system out print line here. And this is a virtual method on print stream, so we're going to get the print line method, returns void and takes a string. That's the one we're interested in calling. Now we have a handle that represents calling print line on an output stream or print stream. And actually in Java 9, they've started to use method handles to optimize string concatenation. So we can do something similar here by just grabbing a handle to the string concat method. And then whenever we call, and actually here we'll bind it to the hello comma string. So we have a method handle that will take hello comma and an incoming string and concat them together and return the result. So we're really building up these little functional objects with multiple layers of logic, manipulating arguments and so on, but we still have a single callable method handle that we can use. We can go even farther than this. There's a number of ways in the API that we can combine method handles together. So many handles can wrap 2 or more. That allows you to do these, what are called combinators, method handle combinators. These allow much more complex adaptations, so we can do branching logic and exception handling logic and so on. But again, the magic here is that no matter how complex this logic, the JIT will still be able to see through this chain of handles, optimize it, and compile it down as if it were just plain Java code. So let's look at an if-then-else sort of case. Here we've got a sort of a mini cache that we're doing. We've got a little hash map. If the cache already has this key, then we just get the result. Otherwise, we want to process something, load some data from a database, and stick it in that cache as well. If we're using an if-then-else, the feature in MethodHandles is called MethodHandles.guardWithTest, and it takes 3 other handles. It takes a condition, which is expected to return a Boolean value, a then body, which can just execute the code, it passes the arguments in, or the else. And so we have the 3 pieces that we need to do this code above. Now let's see what that looks like here. All right, so we've got our condition. In this case, we're going to use the contains key method off the map. So we get our virtual method contains key, returns a Boolean, and accepts an object. And we're going to bind it to our cache object. So now we have a condition handle that has a hash map already stored in it, and knows how to check if a key exists. Our then branch here, we're going to use the get. So we know that the key is in there. We're going to get it and return it. That method type is returning object and accepts an object. So we've got our key. We can pass it into the cache. And again, we bind it here. So we now have a method handle that has the cache built into it and can get a key out of it. And then we have our else branch. So if it turns out that there is no key in there, we're going to use the cache from DB method that I have in my little sample code here. In this case, just a simple static method that will go get data out of the database, stick it into our cache, and it all carries it along together. And so with the 3 pieces together, we now have essentially this code from the previous slide in a single method handle. And that's pretty cool. We don't have to generate any code, and we can build this sort of thing programmatically. That's the magic of it. We don't have to write this code by hand in Java. We can do it based on user classes that are coming in or data that we've got from a database. All right, let's get through this again. Okay, another example. So this is another way of doing a conditional branch here, doing a try catch. Not too surprising, MethodHandles.catchException. It takes a body of code that you want to protect with exception handling. And then a handler. And actually there's a typo here. There's supposed to be a catch exception with a type. So you could say catch exception all throwables or a specific class type there. But the interesting bits are the 2 handles here. So here we have our body. In this case, it's just going to be that cache from DB call. So if an error is raised when we go out to the database, then we want to go into the exceptional branch. We have our handler, which is shown at the very bottom there. In this case, we're just going to insert into that cache an error message so that we can go back later and look and see what happened when we were trying to populate our little mini cache. And the JVM will handle caching the exception, calling the appropriate branch, and then returning or continuing to re-raise it depending on how we do it. Here we obviously swallow the exception and just store an informational value in there. And of course, there's many more adaptations that I'm not going to go into a lot of detail. You'll see some of them in other examples here. We can insert and drop arguments, not terribly complicated. If, for example, we wanted to have our print line always call against the error stream, we can just insert the error stream into that handle. Permuting arguments. If we've got 2 APIs we're trying to bridge and we need to reorder the arguments in a particular way or drop a few arguments at a time, we can do that. Filtering arguments. So you can say, take this handle and pass the first argument into it. Whatever the result of that call is, that's the new argument going downstream into the rest of the handles. So if you wanted to take all the arguments in and toString all of them and then continue to call forward, that would be a way that you could filter them. Similarly on the return, if you wanted to take a raw object that was being returned and toString it or pass it off to something else, you could filter it on the way back out. And then fold arguments, maybe the more conceptually difficult one to understand, but all of the arguments you're passing into invoke would go into this function you give. Whatever the result is added as a new parameter. So now you went from 3 parameters to 4 parameters based on the result of some fold function that you passed to it. All right, so let's put this all together now, and we'll actually make a single handle that can do our little example. So we have our stream getter. We're getting system out, which is the print stream. We have our name, which is the incoming argument. We want to get the person's name that's calling this on the command line. So that's an array element getter. And we're going to always just expect that the 0 argument is the name that we're looking for. So we explicitly bind this array getter to the 0 index. We have our concatenation handle. And as shown before, this is going to be string.concat. And then we will actually bind it to a particular string. So we're always going to be concating onto hello, comma. We have our print line handle. Again, just print stream, print line. And we can fold in, using our stream handle from above, that actual get of the out stream. So now it will go get the stream handle, it will do the print line call, and then we'll do our filter, which basically takes that string that's coming in, concatenates it, calls the print line handle, and does the whole thing as one shot. And then finally the hello there, just to bind the name into the final call to print line. And then we got it. So now we have a method handle that we can call that does all of that logic we showed in our little hello world. Shown a little bit more directly, we load a string from our array. We concatenate that string with hello. Over on the other side, we get system.out. We pull those two things together and call print line. And this is all represented as one callable object that optimizes down to fast assembly code. Okay. So what kind of things do we get in Java 9? Well, largely Java 9 filled in some missing features that those of us using method handles realized we needed for more advanced language integration, for more advanced fun with the MethodHandle API. For example, try finally was one. And I'll show an example of why we needed a try finally rather than just a try catch. Various loop forms. There's lots of things that we want to be able to loop over all values or loop over all expressions in a language. So a bunch of loops have been added to the MethodHandles API. Up until Java 9, there was no way to just directly do atomic accesses on an individual field without going through some utility class. So you get, for example, an atomic integer field updater would be the closest that you could get to this, where you would directly be manipulating a field, not necessarily going through an atomic object, but it's still not quite as direct. People would go into unsafe and they would use compare and swap directly to try and reduce some of that overhead. Now we're going to have ways that we can do that through an API. It still optimizes if you were calling unsafe directly. And then just some little things, like there was no way in the MethodHandle API to directly construct an array. That's been added as a missing feature here. So I mentioned try finally. Try finally is complicated, actually. How many folks know this? That when you compile try finally, the finally block in Java C basically gets copy and pasted into every possible branch. So on the successful path, the normal execution will have that finally code inserted into it. The exceptional path also has the same code inserted into it. And with Java 7 and 8 handles, we basically had to do this composition and copying all by ourselves. So taking something that looks relatively simple, where we have the target that we want to invoke, the body that we want to protect with a finally, and some post logic, some finally logic we want to invoke, that ended up being code like this. Huge. And this is actually using the InvokeBinder API I mentioned before, which shorthands a whole bunch of this code. It's still an entire page just to represent a try finally properly because of that duplication, because of all the argument manipulation we had to do. And this was really painful because I needed try finally logic in JRuby to do pre and post method stuff. This was not going to fly. Now in Java 9, thankfully, all of this logic, all of this noise that we have is basically just boiled down into MethodHandles.tryFinally. And it will do all the extra smart logic of handling the finally logic on the normal path and on the exceptional path, and this is all you have to write. Much better. Loops. I'm not going to go into great depth on the loops here. We all know how loops work. We've got a while loop in the handles API now with an initialization handle that will set up some state, a condition that will return a Boolean each time, and a body that will be executed as long as the condition is true. Simple enough. We can also do it the other way, do while, where we run the block first, and then we start checking the condition. We can do a counted loop. So if we know a specific number of times that we want this handle to execute, we can set up the count, we can initialize our state for the loop, and then the MethodHandles API handles doing those calls for us. Similarly, if we know that we have an iterator from a list, we can just put that iterator in there. The MethodHandle API will handle calling the iterator and terminating the loop whenever it's done. And these are all basically special case versions of the general MethodHandles.loop call. If you want to go and look at the pages of documentation on how this actually composes all these together, it's interesting. But generally, you'll want to use one of the simpler ones like the while loop. So I mentioned the better ways of accessing variables in Java 9, and that's via the API of VarHandles, kind of a subset API of MethodHandles here. So what we get in VarHandles, first of all, we can access fields and arrays. We could do that with MethodHandles before, but this gives us a little bit more direct access. We can do volatile operations. We can do volatile reads, volatile writes, specifically on those fields. And again, it will JIT and inline as if we were doing the unsafe call from Java 8 or earlier. We can have views of byte arrays or byte buffers. So for example, if you're reading in 64-bit longs from a binary data stream, currently you have to read them in as bytes. And then you have to compose 8 bytes together to a long, and then process that long value. It's more cumbersome than what you can do with these byte array views, whereas you can say, take a look at this byte array, treat it as if it were longs, and then you go directly through at an 8-byte stride when you're working with that data. And of course, this is part of the MethodHandle API. A VarHandle can be just used directly as like a Java lang field, or a Java lang reflect field, or you can convert it into a method handle, integrate it into the rest of a handle tree. Walking through how this looks, it's fairly similar to the way that we would do methods and fields with pre-Java 9 APIs. Here we're getting instead of just getting a static getter, we're getting a static var handle for system out. Of course, the same thing we've got for virtual, for instance fields. Here's our byte array views. So we want, in the first case, we're getting a byte array view that will represent everything as an int. And internally, the JVM will do a 4-byte stride when pulling chunks off of that byte array. So with an int array view or a long array view, we can cut the amount of processing and back and forth to that array by 4 or 8 times. It's pretty good. Much more difficult to do than before. Again, people used unsafe tricks to do it. We've used unsafe tricks to do it. Now we don't have to. That makes it much faster and it integrates better. And then, of course, there's array values that we want to be able to access. But up to now, we haven't been able to do easy volatile writes, atomic writes into arrays without using utility classes, without using one of those atomic array reference things. Now we can actually get a handle to an array and do volatile writes and reads directly into it, do atomic reads and writes directly into it. Here's some atomic and volatile access. So we have our stir array var handle here, and we can do our compare and set against an array value. This is just a plain array. We don't have any extra logic here that we need to throw in, like atomic array stuff. We can just do that atomic operation directly against the array. And then, like I mentioned, volatile writes and various levels of memory barriers that go along with this, weak, volatile, and so on. Here is an example of reading in some long values, like I mentioned. We read in our data from some I/O stream. We figure out how many chunks of longs we have here, and actually dividing wrong there, divide by 8, data.length divided by 8, and then we can move at a long width, a long stride, through our data and process the information much more quickly, rather than having to build those long values by ourselves each time. And as I said, you can convert it into a method handle. Unsurprisingly, the method is the thing you call is toMethodHandle, and then you say what kind of operation you want it to be doing once it's invoked, whether it's going to be a volatile get or a regular write, something along those lines. Here we're throwing that into a guard with test, so we're checking a log-enabled Boolean field. Once it flips, we want to concurrently know that the log is now turned on. Now we'll start calling the log path and actually printing stuff out. All right, so InvokeBinder. Now I said InvokeBinder was my way of remaining sane when I'm working with the MethodHandle API, and that's because this code sucks. I wanted to walk through this step by step before to show you how this works, but if you approach this and try to read through it, it's really cumbersome. There's a lot of repetition of types. There's a lot of kind of working backwards. We have to wrap handles from the endpoint rather than the direction that we call them. So what else? What do we have in InvokeBinder? So the problems we have here with method handles getting composed in reverse with lots of repetition, InvokeBinder takes a lot of that and simplifies it. Rather than building backwards from print line, you can start at the top. You know you've got an array of values. What's the next thing you want to do? Well, you want to pull an element out of that array. What's the next thing you want to do? You want to concatenate it, and then you want to get the outstream, and then you want to call it. So with InvokeBinder, we can do that in the natural direction. The forward direction that we would write in Java code, we can do with method handles. So all of this code becomes infinitely more readable as this code. And we can walk through this very quickly here. First, a note on this binder class. This is the main magic class in the InvokeBinder API. We start out by saying what our starting type is, our starting method type. So in this case, we don't expect a return value, but we are passing in an array of arguments, the arguments that were passed to main. We can do all of our manipulation, dropping arguments, inserting arguments, and so what, in just a forward calling direction. Again, all the folds and whatnot, we can have pass in a handle that we know about already, or we can do it as a lambda. And then eventually we can, at the bottom of our binder tree, we can do our invokes or our field operations. So walking through this from the top, we're starting out. We know we're going to pass in a string array, and we're not interested in the return value. It's just a void return. So that's where we start with our method handle chain. We are going to do an array get of the 0 element. So we filter that string array by pulling one value out of it. Then we filter that string again by concatenating it. So we stick our hello string there. We call concat. That's now the new string at this argument. Now we want to fold in the print stream, so we drop all the arguments. We know we don't need them to go get system.out, and we just grab that field out of the system class. And now that becomes the first parameter to our method handles. And then we've got our first parameter, which is the print stream, our second parameter, which is the string that we've concatenated. Now we call print line. And then we get a method handle out the back, and we can do our call just like we did with the longer, messier version using the standard API. All right. So I promised that we might try to do something crazy with this. And leading up to this talk, I started thinking, okay, well, we've got all these new additions to the MethodHandle API. Maybe we're actually Turing Complete now. Before Java 8, we were almost Turing Complete, but we didn't have loops. We didn't have backward branches. Makes some of those things a little bit more complicated. So let's look at this. We can modify state, which is a prerequisite. We have to be able to get some sort of a result out of this system eventually. We can call methods, so we can pull in other code from the system. We can insert conditional logic, so we can do branching logic based on that data that we're pulling in or data that we're modifying. Now we can execute controlled loops, so we can go in circles around code, executing conditions and bodies multiple times. And so now really we can take method handles and represent any language entirely with a handle tree. And it will all be optimized, it should all be optimized, all the types will be checked, and it'll actually compile down and turn into native code. Let's see if this will work. Now I'm a JRuby guy. I've written a couple different compilers for JRuby. I do most of the performance work on optimizing it, finding ways to trick the JVM into optimizing stuff the way we want it to. So we're going to take JRuby's syntax tree that we've parsed. We're going to convert each syntactic element into the equivalent method handle operations. We have some local variables that we need to store somewhere. In this case, I'm just going to create an object array. We'll pass that through, and that'll be our mutable state. That's where our variables will go. And right now, all I've really got working is simple numeric operations, conditions, and loops. But it's sufficient to do fairly complex numerical algorithms already with just a very simple implementation. Here's the main. I don't expect you to read through all of this. I've got this looping parameter in here that I use to force it to run multiple times. I was looking into how well the JVM is doing the optimizations. But basically, we take in some code from the command line. We parse that code into an AST node, which will be a tree of nodes there. Then we start walking through our nodes. Each one will call back into our compiler using that visitor pattern that Ted mentioned yesterday. So just the basic preliminary here. The compile, very simple, just tells the node to do the visitor pattern and accept and call itself back. Here's a version from the call node that will call back into our compiler. So there's the visitor pattern in a nutshell. Some simple constructs in the language. So here we have a false node and a true node that represent a literal false and true in our Ruby syntax. And these we just insert the Boolean false, Boolean true objects as constants directly in. So now we have handle representations of a constant true or constant false value. Similarly with fixnum. Fixnum is Ruby's 64-bit integer type. Since I'm just working with objects here, I will just insert a constant long object into that. Now I have a method handle that represents a constant long object. Working with our local variables. Accessing the variables, pretty simple. We saw array gets before. We know what index this particular variable is at in our local variable array. All we have to do is get it. The set is a bit more complicated here because we need to execute the value. We need to evaluate the new value that's going into that local variable, and then we need to insert that, keep that value around, and return it. So a little bit more juggling of values, but essentially the same thing. Evaluate some code, stick it into this array, return the results, and now we have handles that represent local variable operations. Here's a condition. Very simple again, just guard with test. We've got our 3 branches, a condition, then, and else. We stick them into guard with test. Now we have a handle that represents a Ruby if syntax in our parser. And almost finally here, we have a while node with a predicate, which is our condition that we're going to check each time, and a body of code. We take those pieces, the predicate and the body, and stick them into either a while loop or a do while loop, depending on which kind was parsed out of the Ruby code. And finally, the last piece here, so I've got my root node. This is where we set up this, we compile the body of the script, we construct the object array that holds all of those local variables, and we fold that all together. Now we have a single handle that represents that entire Ruby script with all its conditional logic, all of its calls, all of its loops and other magic. So, does it work? Well, the simple answer is yes, it does work. Here is you can see the output from main here where we print out the AST for this simple code, this simple loop here where we're just looping from 1 up to 999,999. So we run our loop, and then the main prints out whatever the last expression was, in this case, the A value. And we get our 1 million down at the bottom. So we've incremented all the way to 1 million, and it executes. Now, more interestingly, this is cool and all, but we could have just run the AST. We could have run the interpreter and done this much. Does it work well? Does this actually do what I wanted and optimize this stuff down? And I'm happy to say that the answer actually is it does do this. And so what we have is we have essentially created a native JIT for Ruby, or for this little toy Ruby language, that completely compiles down to native code. We have made a native compiler for a language without generating any bytecode. And that's what's really magical to me about method handles. Even complex conditions, loops, all sorts of stuff that we do in a language can be represented as a tree of handles. It's almost like a JVM IR at this point, an intermediate representation. And we don't have to generate bytecode. It's all part of the same security subsystem and JIT subsystem, and we've got native code out the back end. Amazing. And that's thanks very much in part. Chris worked on this stuff. Lots of other folks at Oracle and at other JVM companies have been working very hard, because this is what's supposed to happen. Handles are supposed to turn into one piece of native code. And even better, they should turn into native code that inlines into the caller. And that all actually does work today. All right. So now results from this. How practical is this? Like I say, this compiled code into method handles actually does optimize down to native code. In this case, I'm using objects, so there was a lot of extra boxing logic. If I were to do this with longs, or if I was to run this on a VM with better object elimination, like a Graal compiler, for example, it might actually optimize down to just the simplest primitive operations. But it basically compiles to what you would expect if you were to write it in Java code. It takes a little while to get there. So the method handle tree internally will run like an interpreter a few times. It'll get hot, it'll decide this code needs to be optimized a bit more, and does that internal optimization within the method handles. So we've got multiple levels here. The method handles have to optimize, the JVM then has to take the optimized code and run it, and then the JVM has to decide to optimize that code down to native. So it takes a little while. Like if you're doing benchmarking or quick looping benchmarks, you might run something for 100,000 times to get the JVM to JIT it. I had to run it for 1,000,000 times, usually, to get it to actually generate the assembly code I want. So that's kind of a downside. Method handles slow that process of optimizing a little bit, but it does eventually get there. All right, yep, that. So this may be just a toy, but it's rather interesting. It's really interesting that you can do this. You can essentially get the JVM to generate exactly the native code you want through an API without generating bytecode, without loading new code into the system. Just building up this API, you can get these little functional native assembly objects. So some future ideas for this. I am going to try and continue this. I'm going to expand this to not be my little toy language, but maybe be a little Ruby expression compiler. So if I see that a particular method is only a couple lines of code, maybe I don't generate JVM bytecode. Maybe I don't go through my whole process in my compiler. Maybe I just throw it into a few method handles. That becomes a little inlineable chunk that the JVM will do stuff with. I think it'll be useful. Like I say, maybe practical for small methods or for individual expressions, constant expressions or expressions that I don't expect to be too dynamic. I'm just going to keep pushing on this and see how far we can get the handles to go. I already discovered a small bug in the API that is probably going to get fixed in a 9 update here. So this kind of stuff is exercising the API and playing with it a little bit more. It's kind of fun. Hopefully some other folks might get involved and want to try it out too. So wrapping up here, I hope it's pretty evident that method handles are very powerful. It's so much more than reflection. It's an entire intermediate representation, an entire functional tree that can optimize down to native code and fits much better into the JVM's optimization pipeline than reflection does by far. InvokeBinder, I strongly recommend if you're doing anything heavy with method handles or starting to play with the API. It's so much easier to work with this. Far less repetition, and you don't have to do that conceptual flip going backwards from a target handle and doing your adaptations that way. You can do it forward like you write the code. And just play with it. Let me know what you think. Try the API out. Let me know what sort of changes might be helpful. I'm hoping to take this really low-level method handle API and expand it out so it can be more of an expression grammar, an expression library for anyone to use for this sort of thing, without having to go to the low-level nasty details of the API itself. And that's all I have. That's just about perfect. Thank you. Yeah, questions, please.
Ooh. Go ahead. All right.
So the thing I want to do with method handles is to use them as functional operations, convert them to consumers, suppliers, whatever.
Yep.
Particularly for things with VarHandles where it's effectively a variable reference but more exotic. How convenient is it for that and for other operations like currying and things like that? Am I going to just really mess up my program if I try and use or method handles for that?
No, I think those are perfect opportunities to use method handles. The API is kind of cumbersome, but for example, if you're doing it in InvokeBinder, currying is just insert or prepend essentially. Add an argument, and then you get a handle out. It's very lightweight as far as the code goes, and for something simple like that, currying or doing some basic argument manipulation, that's going to optimize down just great. One of the other opportunities I've thought about for using method handles more directly is to optimize some of the streaming API. The streaming API does a terrible job right now of optimizing through method handles because, for example, collect sees thousands of handles. It doesn't know which one to inline, doesn't know which one to optimize. But collect itself is a trivial a set of expressions, a trivial operation, to just iterate over and do this collect. We could represent collect itself as a method handle tree, insert that where the call would have been, each place we need it, and now we can inline all the way through the method handles too. So there's lots of cool stuff that we could do with this. And that sounds like a perfect opportunity, yeah.
So assume I'm not a language designer, right? I'm not Charlie, because you have a much better beard than I do.
Yeah.
What do I want method handles for that reflection can't do for me already?
Right. So I would say anywhere that you're doing reflective calls or reflective accesses that you need to be on a hot path. This is an automatic move. Reflection, it'll optimize internally, but it doesn't inline well. There's lots of polymorphic places in there where it just can't see through the code. So translating your simple method.invokes and field.gets into method handles would be immediately apparent. It would usually inline directly. Other places would be when you need to programmatically adapt that Java lang reflect method. You need to do some argument manipulation and so on, or you don't want to have catch invocation target exception everywhere that you are calling this thing. You can wrap it with that handler right off the bat. So anytime you're building up more complex logic around some reflected target, again, method handles make that fast and a lot easier to do.
Well, that raises my second question, which is to say, when I use reflection and I attempt to access something that I shouldn't have access to, right? There's a security check to make sure that what I'm doing is not illegal in some fashion, violating private boundaries, or I'm attempting to assign a string where an integer should be, et cetera. At what point in the method handle lifecycle does the security check take place to make sure that everything is still valid?
That's a great question, great question. So when I brought up the two different types of lookup, the one that can see everything, private stuff here as well, and the one that can only see public stuff. That private lookup, that magic lookup that can see everything, it does that access check at the point you get the final handle. So it's like with Java lang class, you can get a method object you can't call.
Right.
That does not happen with this API. If you get that handle, you can invoke it at that point. It knows visibility-wise, you had access to pull that handle out of the class, and that access check is now gone.
So it'll happen basically before the invocation at the final part of the acquisition.
Right. You will never get access to a direct handle that you can't call.
Okay. And is that true even if I pass, like if I typo the name?
Yeah, well, I mean, you wouldn't be able to get the handle. It just won't find it.
Okay.
And,
so it's doing some sort of structural check to make sure that the identifier exists.
Right, exactly. And actually there's another subsection of the API where you can what's called unreflect a Java lang reflect method. So you may have a method in hand that you can't call. If you unreflect it, the MethodHandle API will raise the error right then. But it also means that it only has to do this access check once. From then on, the handle just goes straight through.
Okay. Last question from me. If you were contemplating building a language on top of this, so let's assume you want to rewrite aspect J.
Mm-hmm.
What's the advantages or disadvantages of emitting calls to method handles as opposed to emitting bytecode?
Well, the first thing with emitting bytecode is you're doing a lot of the bookkeeping yourself, for one. You need to be loading this into little subclass loaders. You need to be dealing with too much code coming into the system. Maybe you want to re-optimize or recompile. You're doing all that bookkeeping that essentially the JVM can do for you if you hide it all behind a handle tree. Then when the handle goes away, well, the code goes away and everything else goes along with it. You don't have to do as much of that bookkeeping. The other aspect would be if you're working in a secured environment where it doesn't want you to be generating a lot of bytecode, or it's something you just want to restrict, you could potentially use method handles as sort of a safe way of getting the JVM to compile some expressions for you without actually generating the bytecode and having to cheat the security at that point. So that's probably big things, yeah.
Other questions? Yes.
So it's been something I wanted to work on for a while but never got to, and I don't know if you're familiar with the lazy var in Scala.
Yeah.
And there's a proposal with kind of improving its performance. The downside is the the kind of semantics we need to keep causes to have a huge state machine inside there. So it's a huge piece of code, which only runs while it's initializing, because multiple threads hacking on it. And I was thinking if that could be used to kind of get rid of the state machine once I know this is initialized.
Yes, absolutely.
How would I, which APIs would that be? Just swap the method handle people are invoking, but then I need a volatile on it as well, right?
So for that case, I would probably start mixing in invoke dynamic bytecode here at this point. Because invoke dynamic bytecode, you could have it do that bootstrap, that initialization state machine stuff once. Whatever the resulting constant is, will then essentially be at that invoke dynamic site in the code from then on. It will never go back to the code, never doing other access checks or anything. It's now a constant value. And it can be a complex constant value. It can be something, it can be anything you want. But that's basically like a lazy constant that we do the same thing for in Ruby. So yeah, you'd emit an invoke dynamic. The invoke dynamic would call back to your bootstrap. The bootstrap would run that state machine stuff and then provide a result.
Okay, so these APIs are not really on that level.
Well, I
need,
mean,
right?
on the other side, whatever you plug into invoke dynamic has to be a method handle.
Ah, okay.
So you would use the MethodHandle API to represent whatever the state machine does and whatever it produced. That would get reinserted back as the invoke dynamic and then just optimize like it was always there.
Okay, that clicks. Thanks.
That's a great opportunity for this.
Yeah, thanks.
Excellent. More questions? No? Yeah, thanks, Charlie.
All right. Thank you.
Also, I like to mention this because, you know, back in the day when we were working on this, what was it, like 2010? I can't remember, a long time ago. It's almost 10 years. JRuby was the first language that actually used invoke dynamic, and it pushed us, you know, to make the compiler better. So thanks for that.
Thank you. Yes,
And
it was a lot of fun. We
it
iterated back and forth. I would run some code. I'd look through the assembly, and I'm like, Chris, what is that? Get rid of that. That's not supposed to be there. And he's like, you're right. That is not supposed to be there.
Right.
And then he would fix it.
Yeah.
And then I'd find the next one. But it continues. It continues forever. I find stuff still.
Yeah. Well,
But
now I don't
Hey,
care
now
anymore.
it's. I mean, it works.
No,
I mean,
it
I
works
was
great.
amazed. I was amazed.
I'm
This
glad.
thing. It's so good. It's
Yeah,
really cool.
Excellent. Cool.
All right. Thanks very much.
Thank you.
All right. And we got about 5 minutes, it looks like. So 5-minute break. Of course, Steve leaves. Now I get one clip. So.